Thanks, everyone. I'm Dale. I'm from ClickHouse, and I'm going to talk about how we built ClickStack, which is an open source, OpenTelemetry native observability stack. I'm actually substituting for the creator of this stack, Mike Shee. So I'm going to talk in the context of the decisions that Mike made when he was building the stack, and not so much focus on ClickHouse, but the decisions that he made in trying to provide like an open source observability stack. So I will talk about ClickHouse, but I'll really focus on the decisions that he made in terms of choosing a storage engine and why he chose a column of storage. So I'm hoping this is the decisions he made at a UI level. There's going to be a few talks at this conference on ClickHouse, so I'm going to be fairly brief because I know there's a talk after this that's going to cover ClickHouse as well. But ClickHouse, in summary, is a open source database. It was open sourced in 2016. It's an analytics database. It was actually originally designed for clickstream data, but the use cases have broadened beyond that specific use case, and one of those is observability. So it's designed really for aggregations. It's column orientated, but it also provides fast filtering prior to those aggregations. It does support sharding, but also vertical scaling. We encourage people to scale vertically. ClickHouse is designed to utilize all the resources on a box. It's not limited by any JVM. It's written in C++, so you can go entirely vertical, and then you just to potentially petabyte data sets, and then you can have HA, but you can also shard horizontally. And the reason the aggregations are important, because aggregations are basically visualizations in ability. So its ability to deal with aggregations at very large scale, petabyte scale, is important for observability. And you'll see a plethora of vendors out there offering kind of Datadog alternatives. Many of those are proprietary, and many of them under the hood are actually using ClickHouse now. So it's almost become a standard engine for databases, for observability workloads. And it does mainly bias towards immutable data, but does have support now for more efficient updates. So that's ClickHouse. What is ClickStack? So ClickStack is an open source observability stack. The UI layer is HyperDX, and surprisingly, the data storage layer is ClickHouse. And it's an opinionated end-to-end observability stack. So you can think similar to the Elk stack, but with ClickHouse in the middle. HyperDX is Kibana, and OpenTelemetry is Logstash, with providing the collection layer. All the components are open source. ClickHouse itself is Apache 2 licensed. The UI, HyperDX, is MIT licensed, just because that's what Mike chose when he first wrote the code, and he likes the license, but it's also very permissive, obviously. And it's really, so ClickHouse was used by some pretty large organizations, the likes of Tesla, Anthropic, to build their observability platforms, but it's notoriously difficult to actually use. So the idea of providing an opinionated stack that's fully open source is that anyone can just pick this up, run it, use it in one command. So the first decision Mike had to make was choosing a data store. This was kind of a fundamental decision because it impacts the performance and scalability of the stack. And he had a few choices at this point. And his first choice was whether to use a search engine. So he originally was thinking of using maybe a search engine like Elasticsearch or OpenSearch. Now, search engines are great. They've been around a long time. I myself, Elastic advocate, was Elastic for almost a decade. So I believe that the search engines still have a place in observability. They're great for needle in a haystack searches, inverted indices, hugely powerful, especially the language itself is extremely expressive. I think there's nothing more natural than just typing kind of Google-like searches and being able to filter on logs. They struggle when you try to do very wide aggregations over large data sets. That's tend to where they struggle. And they also tend to maybe not be as performant when you've got very large data sets. And they're not really, because you're writing inverted indices, optimized for very fast writes. They're great. They're great for hot data. Typically, disk utilization of inverted indices typically makes it a little bit more challenging to scale them to petabyte scale. So search is one component. He actually considered having a search engine and then coupling it alongside a time series database engine. So Prometheus, obviously 2012, and we've got various distributed versions of that. And then using the metrics engine to basically allow for to provide the aggregation support on metrics. So having two data stores, so we have search, and then we have maybe metrics, and then we have this kind of disjoint stack, which was the really main concern. The other thing that we felt that time series database engines struggle a little bit on aggregations when you go in an exploratory mode. So if you're going for a single time series, very efficient, you can aggregate. If you try to go wide and aggregate across many series, things tend to not be as performant. And then obviously high cardinality is something which means users have to think about with time series engines, either downsampling or pre-aggregating. And Mike really wanted to be able to provide that exploratory experience and that high fidelity experience where you can really drill in. So decided against this kind of disjoint architecture, and then ultimately didn't want to do correlation at the application level. So passing labels around in the application and trace IDs, wanted to try and push that down to the data store. So he went looking for a database, and the mystery data store wanted to be cost efficient, fast search, fast aggregations, and also to leverage object storage natively. So at this point, in order to really not make retention a discussion, like having to think about retention, having to think about scaling disks, object storage really should be central to this data store choice. So his kind of feature list was quite long. So we've got kind of resource efficiency, fast insert performances. He was engaging with companies who are ingesting maybe almost tens of gigabytes per second uncompressed. So we need that fast. We need fast aggregations. High cardinality shouldn't be an issue. We want schema on read. One of the things that kind of legacy, I think, personally of Splunk was the ability just to extract structure at read time is a huge feature and a really powerful thing. So ability to have like really powerful string extraction functions and not have to write scripts to do that. Schema on basically JSON support. Data coming from Kubernetes is extremely dynamic in its labels. So we want the ability for the schema just to naturally evolve. Elasticsearch nailed this. Like it's one of the reasons it was so widely adopted, I think. Full text search indexes, embedded indices still have their place. We want that expressive query language, and then we want support for object storage, and most importantly, it might needed everything to be open source. So he settled on columnar storage, and I should stress everything here applies to column stores generally. ClickHouse is just one column store. Druid, Pinot, you can use anything. I'm going to be passionate about column stores generally versus just ClickHouse. And the reason that column stores are good is because of the way they orientate data. So if you compare to their cousins, row stores, which are like Postgres, for example, would be a classic row-oriented store. Column stores separate things by data. Most column stores also then allow you to order the data by a key. So it's actually ordering the data on disk by that particular key. Then you can add things like codec support. So in his case, we add a codec to just reduce the number of bits. I should say this is actually a Stack Overflow data set. It's just an example with post type and the creation date. And then because you've ordered the data on disk and because you've applied these codecs, when you apply compression techniques like ZSD compression, this reduces the data quite dramatically. And you get a few side benefits from that. So you get the high compression, which reduces your I/O. The compression starts to look sort of 10x to 20x of the original data size, which is great. And then but most importantly, any query language only accesses the columns it needs. So it doesn't have to read the entire row for the data. It just accesses the columns that it needs, which reduces I/O further. Obviously, the filter clause has to access columns and the select clause, but in theory, you reduce the amount of data that you read. Now, one of the benefits of columns is, or in this particular architecture, is that you can stream data in blocks. So you can take ranges in queries, and you can dedicate a range of data to each core on the CPU, which allows you to parallelize filtering, aggregates, and produce what are called intermediate aggregate states. And then you just leave them merging to the final part in the query pipeline, and then you sort and you limit. And because you've got this aggregate ability for aggregate states to be distributed, so you can think of an aggregate state as like a sum is obviously easy, an average would be a count and a sum. Something like a distinct, unique would be more complicated, but it's just a representation in intermediate state of a group by. If you've got those, you can distribute them, and you can distribute this across multiple machines. So what you're actually doing here is when you're issuing a query, you're utilizing the full resources of the machine. The query isn't single-threaded execution, and that is one of the secrets to providing really fast query performance in column stores. And this idea really comes from OLAP databases and the data warehousing space even from the 70s and through to the 80s, and part of commercialized by Vertica in the 90s, and now we've got open source solutions to this. So because the data is ordered, you can also build indices are extremely lightweight. So in this case, this is a ClickHouse example. Columns are very similar in other databases, but we have the order type. We are ordering the data by post ID and the creation date. And rather than having to create an index that points to every single row, because you know it's ordered, you can create a sparse index, which is much lighter. So you just take chunks of data and store the first value for each of the columns. So you can have petabyte data sets, but the actual index in memory is only a few megabytes. So when you actually query that, the benefit there is that you exclude whole blocks very quickly, and you only have to read those ranges, and actually the amount of data you have to read off disk reduces further. So that's another benefit of ordering and storing things by columns. Schema on JSON. JSON actually is quite naturally represented in a column store because JSON is just basically fields. And the only trick that you then need to think about is how do I read the JSON objects and create the columns dynamically? But if you just think of the A column just being a vertical set of values, you can easily represent that. One of the things which This is actually unique to ClickHouse, but I expect other column stores to adopt this, to be honest. And I suspect things like Snowflake do this under the hood, although we haven't got the internal details. But one of the things that was always frustrating me about Elasticsearch was when you send a document, it determines the type of a column based on the first document it sees. I think the superior way of doing this is to store the type field pairs. So if a column comes in A as a string, then later it comes in as a numeric, why not store two separate columns? And that actually gives you can exploit that to do all the delta encoding, all the codecs, all the compression techniques that we talked about earlier. So we actually store in ClickHouse a column per field type pair, but that's a kind of implementation detail. And then finally, object storage, ability to scale compute and store a single copy in object storage and can scale compute both horizontally and vertically. The nice thing about this is you just don't start thinking about retention anymore because you only store one copy. And you can, if you're getting 20x compression, you can store huge data sets. Like we have almost 100 petabytes in our own logging infrastructure, but you can separate, isolate read and writes as well. So you can have very small compute for your write, which is continuous. And then when you do an investigation, you scale up your compute and then you scale it down again. It's just a cost optimization technique. I talked about why fast aggregations. They obviously provide fast aggregations and this fast filtering. And then we've also got, I had not talked about it because I don't have time, but columns. Most of these column stores actually support your ability to specify an inverted index at column level. It's experimental in ClickHouse, but you can also use things like Bloom filters. You can use things like min-max indices, and you just specify these at a per column level. So they give us fast and efficient indices. I've talked about schema on write being effectively JSON, and then schema on read. Schema on read is, it's tied to the last point, which is the query language, which is SQL. Most column stores are wrapped in an OLAP database ultimately, and they support SQL. SQL is great language for data exploration. I'm not particularly a fan of it for observability. Personally, I think it's quite clunky to do explorations in SQL, but it's a great foundation to build on. And SQL comes with a whole plethora of like functions for string parsing that are pretty standard in the ANSI SQL syntax. So you get that, but then you are left with SQL and building an interface on SQL, which brings us, I'll talk about how we address that. But SQL is great for deep data analysis. It's just, in my opinion, not great for just doing casual exploration of the data or running an investigation when you just want to do natural language type search. These are just a couple of use cases, Netflix and Anthropic, which have gone this way as well in order to handle their petabyte scales. So why OpenTelemetry? I'm not going to try to teach everyone here about OpenTelemetry. I think it's pretty much the commoditization of observability instrumentation now. It's the de facto standard. It was an obvious choice. Like, it gives us all of these SDKs. It gives us unified telemetry for logs, traces, and metrics. And the big thing for us was just like both the community is great, and most importantly, it's open source. So that was obviously attractive. I should say that OpenTelemetry isn't just the one size fits all solution. There's people that can't move to OpenTelemetry. We do see the term like kind of wide events coming up. Wide events really quite simply are just logs with metrics on them. Like, you're just packing everything onto a single event, and it's just a JSON event. And Elasticsearch was doing wide events for 10 years. Like, it's just terminology. Like, it's, you just, rather than thinking of things in logs, traces, and metrics, you just collect an event and pack metrics onto it. Again, this fits perfectly into column orientation, so there's no reason. So the UI we're going to talk about, actually just all it requires is a date time, but you can use OpenTelemetry schemas if you want to, and we're auto detect that just to make things a little bit easier. So building the interface, why we need a dedicated interface. So people will use, I think Druid have talked about this, people use Grafana, people use Grafana on top of ClickHouse, they use it on top of Pinot for this problem. SQL is quite tricky to write if you're doing anything more than static dashboards, especially as an explorative language. And the main thing is that most databases will have an analyzer that will try to optimize the query based on what you write, but often you need to understand the internal mechanics of the database to truly get the best performance. And you're quite easy to write a query which is extremely resource intensive. So you do need to kind of be conscious of that, and it's just not accessible for everyday developers to have to go and write SQL. And I can write SQL quite quickly, but I've been forced to learn. And then you forget that, how hard it was to get over the initial bump. And then you're not really sympathetic to new users. The decision that very early was to provide Lucene syntax, so be able to convert, this is HyperDX, the UI for ClickStack, to be able to take a string search and convert that optimally to a SQL statement and transpile it to a SQL statement behind the scenes. And then a decision really to think about, can we explain to the user what this query is going to do so that they don't end up wondering what their query is going to do? And that's inherently built into the UI. And then you always have the SQL, the ability to do filtering. And then we always provide this escape hatch to SQL if you want to do something which is like really in-depth, detailed analysis of the data. Same on charting. We don't expose like the underlying functions of SQL. We just provide a very simple experience. And this is very Datadog inspired in some ways, that all you do is just provide functions in a very simple charting experience. That's just being empathetic to the user and abstracting it away. But the real reason that we wanted to build a UI versus just relying on something like Grafana is that the UI needs to be quite tightly coupled, in our opinion, with the database. It needs to understand the database. A really simple example, and I will go through a few examples to justify this, but token search is searching by a single token can be very efficient because we have Bloom filters and inverted indices. Once we resort to wildcard or subtext searching, things get a little bit more inefficient and we have to scan more data. So the UI is constantly encouraging people to teach search by tokens. So that's the most simple case where we want to encourage these workflows and this user behavior that really doesn't cause inefficient queries. But then there's a whole host of optimizations. So in the UI, when you go to the logs view and we always list logs typically in most observability tooling, most recent logs first. If people have modified their schema, which is very natural to do to optimize for their access patterns, we need to know how to order the data according to the ordering key on disk. And if we don't align how we sort in the UI by the ordering key, we can't take advantage of a number of optimizations in the database. And this is this animation just showing the difference between when it doesn't align, the query takes maybe 1.9 seconds, I think. But when it does align, it takes a fraction of a second. So this is just searching through some random integers, but it provides that here it doesn't align on the first query, it takes 1.9 seconds. If it does align, it takes a fraction of that, so 0.015 seconds. So the key here is that we introspect the schema, we understand the schema, and then we influence the queries we make in the UI. So again, it's a very tight coupling between the database and the UI. Other cases, when we're listing logs and you're searching through logs, we need to understand that certain access patterns are favorable to the database. So in this example, we actually chunk requests and we chunk the time ranges and we load them asynchronously versus trying to stream millions of rows back or hundreds of millions of rows back in a single request. Again, we need to understand the sort order of the disk and make those requests as efficiently as possible to align with the sort key and the primary keys. Other cases, and this is probably the kind of final example, is ClickHouse has a map type. And the map type is basically, you can just think of it as a kind of map, like Java map. It's just like type string, a type value, and it's strongly typed. So you say the keys are types and the values are whatever string. It's historically a great dumping ground for just random arbitrary data. We have replaced it with the JSON type, but there's still good reasons for having a map type. So you can think of like JSON keys as being the key is string and the value is also a string in many cases. The problem is if you read a single key from this map, it reads all of the map off disk. So it streams the whole map off disk and it reads all of the keys. So it's quite IO intensive to access this map. So what we encourage people to do either through the UI and through the database is like materialize specific columns out to their dedicated column at insert time. So this kind of highlighted syntax is basically saying when a row is inserted into this table, take out the referrer and put it into a referrer key. Then when the UI sees that you're accessing a key in the map, it checks to see whether there's a materialized version and reads the materialized version. So again, like we have to couple the UI with the database. Doing this kind of database independent is kind of challenging. So that's really like final optimization layer. So in summary, I think I've made a case for we need to move beyond dedicated data stores per data type. Like I think creating data stores for a specific data type is one way to go, but it ultimately pushes correlation up to the application layer. Why not do it in place where it can be optimized? Like joins are fantastic. Joins offer you the ability to join data, and nothing's going to do that better than a database which has been designed for that specific role. I think column-oriented databases are ideal for observability, whichever one you use. Just the compression is compelling, the read time is compelling, and it just allows you to take away having to think about things like retention. You can just get such high compression, you can store on object storage. I think SQL has a huge place in observability moving forward. I think I would like just kind of caveat that, as I said, it's not the most accessible language for exploration and adoption, but the ability just to connect to your database and use like all of the data science tooling out there and do deeper analysis is quite a compelling story as well. So I think SQL is definitely the lingua franca for data exploration. It's not going anywhere. And then really to exploit this, I think we have to start building custom UIs and hopefully open source UIs for all of these data stores, the new wave of data stores, versus just relying on generic tooling. And I would say that I'm a huge Grafana fan. I think Grafana has a huge place in this, in being able to connect data from different data stores. But I think they has to live alongside dedicated user interfaces for those stores as well. So I think they complement each other perfectly. And that's it. Any questions? I'd say if you want to get started, you want to download ClickStack, you can just get started in one command, and then there's a public demo that you can play with if you're curious and have a play with it. Any questions? I went quickly thinking I didn't have much time, and now I've left myself with hopefully not 9 minutes of questions.
Hi, thanks for the talk. So I saw a presentation from Tesla where they developed PromQL transpiler.
Yeah, they have.
And I heard that ClickHouse was about to develop it. At least it was promised like a year or 2 years ago. And it was promised.
It's now in the first release was made last month. So the very first basic support for PromQL has been released in open source. We chose, rather than trying to drop it as like a monolithic project, we decided to try and gradually expand the support for the syntax over the next 6 months. So you can expect to every release will expand support. The first thing really, the transpiler approach, isn't a great way to go. Like Tesla, they do 1 billion rows a second and they have a quadrillion rows. The transpiler produces some pretty horrific SQL queries. So we've decided to move it inside the database and bring it in as part of the actual analyzer and natively supported in Prometheus, inside PromQL natively inside the database. That is a bigger project, but I think over the next 6 months, you'll see improvements to PromQL support every month. And then there were some functions that we needed. We didn't have things like rate function in the underlying SQL, so we've had to implement those. So they were the kind of first stage, provide the foundations for all the functions that PromQL supports, natively as SQL functions, and now we're building on top. So I think by the end of the year, we should have, or the end of early next year, we should have decent PromQL support.
Okay. Do you plan to be compliant with Prometheus PromQL tests or something like that?
I can't really talk to the level of compliance we will reach. I think the intention is to become 100% compliant. How long that's going to take, I think is a good question. I think I would defer that to the product manager. But the intention there is, the answer is yes, we would like to. But I'm sure PromQL has very expressive language, and there may be things that are just too difficult to implement or provide in an efficient way. But yeah, we would like to be.
Okay. Can I have one more question?
Yeah, of course.
Yes. You talked that it's very important for UI to be tightly connected with the database to benefit from all the optimizations that you can get from it. But most of the users still using Grafana, and not because Grafana is great from the user interface perspective, because Grafana is now like an umbrella for many data sources and user management and authentication and a lot of other stuff. So having the HyperDX UI seems like a new UI that I need to learn when I'm moving from something like Prometheus to ClickHouse. Do you think this UI will eventually be as important as Grafana or as successful as Grafana, or what is the main direction for ClickHouse integration into observability?
Yeah, I see Grafana not going anywhere. Personally, I think they'll coexist. I think HyperDX is very optimized for data exploration. That's not really what Grafana is. But there are things that I think we can push back into the Grafana plugins. There's a Grafana plugin for ClickHouse that you can just use and connect to ClickHouse. There's things that we want to push back into that to also improve the experience there. So things like natural language search should be part of that plugin. So all of the Lucene syntax and ability to do that. Adding Prometheus support, I think, is going to blur that even more, because being able to just connect to ClickHouse with Prometheus, we're not going to encourage people. It's their choice. I think HyperDX is more tuned towards exploratory workflows. Grafana is more for dashboarding workflows. And if you've got multiple data stores that you want to correlate with, Grafana is the way to go. I think there's space for two to coexist, personally.
Thank you.
All right, so one more. Anyone?
Great, thank you.
Thank you.
And thanks for Mark for adjusting the flow, because I have to get back to my house.